yesterday and last couple of weeks, we've been working on standard dosing where we're targeting a concentration, usually a CSS average, right? That we're trying to target. And that may be appropriate for a lot of things, right? For most drugs, we're just gonna shoot for this average concentration that we want to hit and stay close to within a certain range. And then we adjust based upon what we find out in the patient, either through signs and symptoms of lack of efficacy or toxicity, and we get levels and we decide if we need to make any adjustments up, down, give loading doses, hold doses, right? So everybody got that idea. So everybody can do that pretty much, right? Well, that's not always enough. So traditional dosing, like we said, is based upon CSS average target concentrations. We keeping them within, a CSS max and CSS min range usually. We always start with population data, right? And then, so we look up in Micromedics somewhere, or we look up data to figure out how we should start in this patient, which is usually weight-based. Sometimes if the drug is cleared by the kidneys, we might have some changes based upon their kidney function on where we're starting. And then we go ahead and adjust based on the signs and symptoms and measured concentrations. But is it always optimal? The answer is no, otherwise I wouldn't have brought it up, right? So we're going to be talking about some advanced methods, and they're particularly in antibiotics. Now, I want to worry about saying this. I don't expect you to master this. I mean, we're just going to talk about it today. It's just an introduction. We will be doing some case examples and some problems in the second hour. But for now, I just want you to kind of sit back and listen, but you're going to need to draw on everything you know about pharmacokinetics to understand this discussion, okay? So you all have had the basic foundation to understand these dosing dilemmas that we get into and how we've solved them and how we're working on solving them, okay? So just don't worry about taking a lot of notes, just sit back and listen. I will ask you a couple questions on the final on this, but it's more of, I want you to get you ready for your next step, which is doing more advanced dosing, okay? And you will get a lot more instruction in this next year and in your your second and third professional years, and certainly out in practice in your fourth professional year. But I wanted to give you some foundational information. It's going to be very surfacey, but I want to make sure that you understand that it's just an application of what you've already been doing. Okay, and an understanding of what you've already been doing. All right. So we're going to talk about the pharmacodynamics of antibiotics. Now, I mentioned this when we were talking about pharmacodynamics, but I think I had one slide and I said, don't worry about this for now. Well, now I want to come back and worry about it a little bit, all right? Because what's interesting, I find this very interesting, I hope you do too, but most situations we're really just dealing with the drug and the patient and receptors and such that we have to understand and regulate. When we're talking about infectious diseases, we've also got a third party involved, right? We have that bug that we have to think about what that bug is doing and how do we optimally deal with that bacteria or virus or whatever the infectious agent is. So it's a third party, an outside party that's involved here, right? So we have to think about all three of those things, the drug, the patient, and the bug, okay? Which is one of the reasons infectious disease is so interesting. Actually, when I was in pharmacy school, I thought I was going to be an infectious diseases specialist because I thought it was fascinating, and I still do. But I think you will too. Are any of you guys signed up to take pre-ID? I recommend it just because it's so much information. It just helps you get a little jump start getting ready for the spring, which is when you'll be taking the class. Okay. So we have to think about the bug as well in this case. So we found that through experimentation that there's different goals based upon the type of bacteria and the type of antibiotic that we're using. Some antibiotics are what we call time-dependent killers, and some antibiotics are what we call concentration-dependent killers. So you can tell by the title probably what that means, right? So time-dependent killers, we want to keep the concentration above a certain concentration that's above the MIC. What's an MIC? You're all in micro or hand micro, right? What's an MIC? Crickets? Really? Nobody knows? Or are you just too shy? Is it like in France when no one will speak English, even though they all can speak English? No? Minimum, this is really important. If you don't get this out of micro, I don't know why you're taking micro, but that's okay. That's just my view of it. Minimum inhibitory concentration. What do you think that means? A lot of these things are named nicely rather than after the person that founded it, which is nice. What do you think minimum inhibitory concentration means? Yeah, the minimal concentration of drug we need to have in the body to inhibit, not kill, but inhibit growth. You have to know that. MIC, minimum inhibitory concentration. The very least we need to have around to inhibit growth. Notice not kill, but inhibit, okay? So with time-dependent killers, we want to make sure that there's a minimum amount that's above the MIC for your dosing interval. That's how you kill the drug. So I call this the radiation or annoying neighbor. So radiation, annoying neighbor, they're just kind of at a low level of annoyance just to keep you annoyed all the time. I don't know, you probably never had that kind of neighbor. Probably I was that kind of neighbor, I don't know, but just that constant, nobody's laughing today. Am I not funny? I guess probably not, but what's another thing for this constant that finally, that's stopping the drug from, or the bug from being able to thrive, right? Those are called time-dependent killers. So these are usually beta-lactam drugs, which you probably don't know what that is yet, but it's penicillins. You've heard of penicillin. So all the penicillins, cephalosporins, have you heard of cephalosporins? So the penicillins and the cephalosporins, which are beta-lactam drugs that attack the cell wall, they are time-dependent killers. So you don't have to worry about getting big levels, right? You're just worried about keeping a relatively annoying concentration around for that bug. Okay, so what do you think we're going to be targeting then? We'll get back to that, but well, we're going to try to keep our free concentrations above the MIC for a certain percentage of the dosing interval. Does that make sense? So that's time above the MIC is really what we're shooting for, probably. In some cases, we're shooting for an area under the curve over the MIC. So you can see here we have a picture of, can I write on this? I never, yeah, okay. So here's our curve and our area under the curve. You know what that is, right? And notice here is our MIC. So the area under the curve over the MIC is this part here. Because when we're under the MIC, we're not really annoying the drug, are we? So we're really concerned about this area under the curve over the MIC. Okay. And how long or what percentage of the tau we're above the MIC. So you can see if our tau goes to here, we're only this much. So what, about 2/3 of it is over the MIC. So we're using different targets. We're not looking at CSS average here, are we? Do you follow this idea? That we have to consider how we're killing the bug? So we want to keep, and notice this is free concentrations, because the only active drug is the free drug, above the MIC for 30 to 70% of the dosing interval. So time over the MIC or area to the curve over the MIC are going to be our targets here, aren't they, rather than a CSS average. The other drug that's important here is vancomycin, which is what we're actually going to be dosing in a few minutes. So vancomycin also is a time-dependent killer. Some drug-bug combinations are a little bit of each, but usually we can put them in one camp or another. Okay. How do I? Okay. And how about concentration-dependent killers? Concentration-dependent killers are the other end of the spectrum. Concentration-dependent killers rely on high peak concentrations to knock out the drug. So I think of this as a prize fighter. You gotta get that thing. Give him a punch. So here that peak concentration becomes important, doesn't it? Not so much the annoying, but getting those peaks nice and high. So we know we want more than 4 times the peak concentrate, 4 times our MIC for the peak, and some people say up to 10 times the peak or the MIC for your peak concentration, but we want as high a peak as we can stand without toxicity. Okay, so those are concentration dependent killers. Now these are more about inhibiting protein or DNA synthesis, which is how the drug works, okay? Again, you don't need to know that yet. You will a year from now, but not yet. So these are observed for aminoglycosides and fluoroquinolones. Aminoglycosides are drugs like gentamicin, tobramycin, amikacin. You probably haven't heard of them unless you've worked in a hospital. We're going to talk about the aminoglycosides today. It also is seen with fluoroquinolones like Cipro. You know Cipro, I'm sure, ciprofloxacin. Okay. So here we're looking for a Cmax to MIC ratio. We want that to be as optimized as possible, don't we? The Cmax to MIC. So as that MIC goes up, right, the effectiveness of the drugs go down, doesn't it? That's what the MIC is telling you, is that I need more drug. If you go from an MIC of 1 to an MIC of 2, that means we need double the amount of drug to do the same thing as it was doing before, right? And as you probably have read and heard in our society, the bugs that we're seeing are becoming more and more resistant, aren't they? So you have to really pay attention to MICs. And MICs will vary in your patient to patient, day to day. There will be trends, if you're working in a hospital, there will be trends in your hospital where you know that all of your whatever bug is very resistant to gentamicin or to this drug or to that drug. It tends to, because you're all sharing germs because you're all in the same hospital, it tends to be in hospitals. And most, I shouldn't say most, every hospital I worked in, probably depends on the size of the hospital, but we had a review of how resistant every bug was in the hospital so that we knew what drugs were and were not likely to work if we saw them in our patients. It's called a bacteriogram, but all right, I'm getting too deep. All right. These drugs also exhibit a post-antibiotic effect, which I'm not going to talk about too much other than to say, again, it's named well, that even if the concentrations fall below what we think is the inhibitory concentration, like the MIC, they still seem to have a longer lasting effect than we would predict. So there's something else that's happening. It's probably because it's happening at the protein synthesis stage that the effect goes longer than the drug is actually above the MIC. So we use that so that we can get a really high peak and have a longer tau than what we might have thought we could, so that we can avoid toxicity. So interestingly, how I've always said, most of the time we want to have the drug act like a constant infusion. Most of the time we want it to hug the CSS average, right? We want it to just stay consistent for most drugs. Aminoglycosides are the opposite, right? Because we want a really high peak, because that's how it's effective. And we found that if we don't let the body have a drug-free period, we get nephrotoxicity. So we want there to be time for there to be very little drug. So we want a big peak to trough ratio, which is the opposite of every other drug, isn't it? Are you following me on all this stuff? Like I said, I don't expect you to really be able to repeat any of it at this point, but I want you to understand what I'm saying. So we have different goals, right? When I started learning about this, to me, it was a revelation, because it's like, oh, so we have to really think about the situation and what we're doing, right? As far as how can we be most effective with our drug therapy? We need to understand how the drug bug combination works, right? And figure out what are we going to do to give that the best chance to work. That's the case with chemo too. What are we going to do to have a best chance for that drug to kill that cancer cell and not kill everything else, right? So understanding that gives us a big advantage in understanding how to help patients do well. So for a concentration dependent killer, we're looking at the Cmax to MIC ratio. So the difference between the MIC and what we're achieving for our maximum concentration. We want to optimize that, right? Does everybody follow that? So this would be for our concentration dependent killers. This would be for our time dependent killers, right? This would be for our time dependent killers. Notice none of these are CSS average, are they? That's why I wanted to just, after we mastered the CSS average stuff, I wanted to take a step back and talk about these different goals now. So how are we going to help our patients achieve this?